Thanks very much. We're going to move to the next speaker, Noor Seijdel. Noor is also postdoc at the Vrije Universiteit Amsterdam, working with Martijn Meta, and she combines neuroimaging, behavioral experiments, and machine learning to study vision and vision in the brain and machine vision. So I'm really looking forward to her presentation. Welcome, Noor.
Thank you. Can you see my screen? Good. Okay. Yeah, so thanks for the introduction. My name is Noor, and today I will present a study in which we investigated the need for recurrent processing during visual object recognition. And today I will present data from behavior, EEG, and deep neural networks to argue that this depends on the need for scene segmentation. So object recognition has been studied for a long time, and because people are so fast and efficient at, for example, recognizing this dog, it has been argued that a first feed-forward sweep of visual information might be enough for successful recognition. And while this might be true for this dog, recently a multitude of studies using more naturalistic scenes have suggested that recurrent processes might be employed more adaptively, so depending on the visual input. So while feed-forward activity might be enough for very simple scenes with isolated objects, such as this dog over here, for more complex scenes or more challenging conditions, so for example, objects that are partially occluded or degraded, additional visual operations that require recurrent computations might be needed. So for simple scenes, rapid recognition may thus rely on this coarse and unsegmented feed-forward representation, while for more cluttered images, recognition may require extra visual operations to, for example, group parts of the object together and to segment this object from the background. And several studies have already shown more indirectly that the segmentability of a natural scene might influence the degree of recurrent processing. So for example, in this study from 2014 by Mika Koivisto and colleagues, they reported that masking, which is a technique shown to affect mainly recurrent but not feed-forward processing, was more effective for objects that were rated as being difficult to segregate. And also in a more recent study, we showed that natural scene complexity indexed by 2 natural scene statistics modulates the degree of feedback activity. And interestingly, these 2 parameters, they provide information about the segmentability of a scene. So in this complexity space that you see over here, simple images containing one or a few easily segmentable objects are on the lower left, while images with a high degree of fragmentation end up on the upper right. So these 2 studies seem to indicate that recurrent processing plays an important role during figure ground segmentation. However, both these studies, they did not test for effects of segmentation explicitly, and they used natural scenes that were uncontrolled, so in which complexity could correlate with other contextual factors in the scene. So therefore, in the current study, we wanted to systematically investigate whether scene complexity influences the extent of recurrent processing during object recognition. So to do this, we went for a more hybrid approach, in which we showed objects in isolation or superimposed on 3 categories of phase-scrambled versions of the real-world scenes, still corresponding to the complexity properties of the naturalistic scenes that we used in the previous study. So by generating the stimuli in this fashion, we combined relevant features of objects in natural scenes, embeddings with different levels of complexity, with a design that is more controlled. And importantly, each object was presented in all conditions, allowing us to attribute the effect of complexity or segmentability of each trial and rule out any object-specific effects. So basically, our aim was to see whether we need more extensive or recurrent processing specifically for these more complex images. So to this end, participants performed on a 5-choice categorization task in which they had to differentiate images containing cats, birds, fire hydrants, frisbees, and suitcases as accurately as possible. And in half the trials, we impaired feedback activity with visual backward masking. So in addition to behavioral measures, we also measured EEG responses to examine the time course of visually evoked activity. We used an we used a setup in which we split the data into an exploratory and a confirmatory data set, so that we could use this first data set to explore, but also to define our electrode selection, pre-processing steps, and time windows for further ERP analysis. So then in this confirmatory data set, we looked whether we could replicate these results both in behavior and in the ERPs. So I will first show you the behavior. So basically, results indicated that apart from main effects of both scene complexity and masking, there was an interaction effect, indicating that masking impaired performance for objects presented on more complex backgrounds stronger than for less complex backgrounds. So this is what we expected. So if you need recurrent processing for these complex images, you expect it to suffer most from backward masking. And if we look at the confirmatory set, we see again the same pattern of results. So then to the ERPs. To investigate the time course of figure ground segmentation in visual cortex, we pooled the evoked responses to the masked and unmasked conditions across occipital and peri-occipital electrodes. And as you can see over here. And what you can already see is that here you see the 4 different conditions. So what you can see is that they start to diverge at some point. This is easy to see for the unmasked condition, and for the masked condition, it's more difficult also because we see a very clear effect of the backward masking. So what we did is we generated difference waves by subtracting the signal of each condition from the segmented condition. And doing so enabled us to eliminate the effect of masking and to only look at the differences between the low, medium, and high complexity scenes. So then, because this was our exploratory set, we used this data to define different time windows. So what we did is we performed t-tests on every time point to see whether the signal was different from 0. And then, based on these significant time points, we defined 5 time windows. You can see over here. So we have a very early window, around 100 milliseconds, and then 4 later time windows. So then we repeated this analysis for the confirmatory set, but now in the confirmatory set, we could look at these different time windows to see whether there were different effects of complexity and masking. So here we see that the data looks quite similar, but now if we look at the average ERPs in these different time windows, we see different patterns emerge. So crucially, what we see is that main effects of complexity only start to emerge in time windows 2 and 3, indicated with an asterisk below the time windows. And importantly, we only see an interaction effect, indicated with an X or a cross, appear in time window 4, indicating that masking impairs performance ERPs differently for different complexity conditions, only late in time. So then we presented the same images to deep convolutional neural networks with different architectures to more directly test whether different feed-forward or recurrent architectures perform differently on these stimuli. So first, to investigate the effect of recurrent connections, we tested different architectures from the CORNET family. And in the CORNET family, we tested 3 architectures: CORNET Z, which is a feed-forward architecture, CORNET R, which is a recurrent version, and CORNET S, which is recurrent with an additional skip connection. And then, to further evaluate the influence of network depth on scene segmentation, we also showed these images to 3 different ResNets, or residual networks, with increasing number of layers. And here we see the results. So in line with human performance, results indicated a higher degree of impairment in recognition for complex backgrounds for feed-forward, as you can see for the CORNETs, and slightly less clear for more shallow networks, as indicated by the ResNet performance. So we have 3 lines of evidence showing that recurrent computations are critical for recognition of objects embedded in more complex backgrounds. So first of all, we have behavioral results indicating poorer recognition performance for objects with more complex background, but only when feedback activity was disrupted. Secondly, we see EEG measurements showing clear differences between complexity conditions in the ERPs quite late in time, after this first feed-forward visual sweep of activity. And finally, we see that deep convolutional neural network performance confirms this, showing that feed-forward networks show a higher degree of impairment in recognition for objects in complex backgrounds compared to recurrent networks. So together, these results support the notion that recurrent computations drive figure ground segmentation of objects in complex scenes. So for this dog, when presented in isolation, perhaps a feed-forward sweep might be enough, but when it's presented in a naturalistic background, that could be different. Thanks, and also to my colleagues and for Neuromatch for organizing this event. I'm happy to take any questions.
Thank you very much, Noor. That was a really nice presentation. I really enjoyed it. We don't have questions from the audience yet. I encourage everybody in the audience to ask questions either on the chat or on the Q&A tool, and I will ask it for Noor. In the meantime, so I've been following all this personally, all these new results showing evidence like you did also very neatly with behavioral and electrophysiology and so on, showing evidence that the recurrence is necessary. So how would you explain this fact? So on a higher level, why do you think that recurrent processing is especially necessary for processing complex scenes, complex backgrounds in the case of
So I think that for these very simple scenes or yeah, I don't know, isolated objects, it might not be important that we know exactly where every part of the object is. So there, just this first very coarse representation is already clear enough or distinctive enough for your brain or for you to recognize what is shown. And for these more complex images, yeah, this might be a too noisy representation, or there might be conflicting features. And there, it might become more important that you know exactly which parts of the image you need for the task at hand. And yeah, we know that recurrent computations are involved in encoding these more fine-grained, detailed spatial relationships. So I think that's why we see this difference.
Mm-hmm. Cool. Thank you. And I mean, my intuition is as well that, so in general, we don't normally see a lot of we don't get a lot of visual input without much complex background. So we are constantly processing complex scenes. Do you think that it will be able to possible to show evidence of recurrent processing as well, to show to understand complex backgrounds with more natural images and distinguish?
Yeah, so I think this research really shows that it's important to also use natural scenes in your research, because the results can be quite different from all these previous studies showing, for example, these isolated objects on gray or uniform backgrounds. I don't know what your question was exactly, but
yeah, I was a bit distracted.
That's okay.
No, I wanted to ask that. So in your experiments, you are using this kind of artificial synthetic background, I would say. So I'm wondering if you have ideas how to reproduce this sort of experiments, which I find great, with natural images, for example, with.
Yeah, so So in a study before, we did use naturalistic scenes, and there, we noticed that it is quite difficult to attribute the effects only to the difference in background, for example, because of course, with naturalistic scenes, there are just many other factors that correlate or vary along with the complexity of a scene. So I don't know, what you could do is maybe try to generate more, I don't know, synthetic, or generate scenes that are naturalistic, but in which you have still control over for example, what other objects are seen, are invisible, or yeah, you should, then you have to very carefully select your stimuli, and
yeah, exactly. Yeah, it's a complex.
Maybe using virtual reality scenes or virtual environments, something like that, then you would be able to better control this.
Yeah. Okay, I think we need to move on. Thank you very much, Noor, for your
Thanks a lot.
presentation. I'll keep an eye on